start, I guess?
Yeah, please start.
Okay, so I think the last thing I was doing was index. So here I have A contained in B. There are two unfactors. This is the left Vaughan dimension of L2B. Remember, two unfactors have unique traces. That's great. Okay, so this is the index, and we saw that the index had some nice properties under direct sum and fusion. And I gave a few examples that Yasu had already talked about. So now we can talk about what it means for a bimodule. So all our we were working in the two category of finite but Neumann algebras. Now we're only going to allow the objects to be two unfactors for technical ease of the exposition. Okay, so now every time I'm writing A and B, they're always two unfactors. So definition. We call this bimodule bifinite if the left Neumann dimension and right Neumann dimension, they both have to be finite. Okay, so really this right Neumann dimension is the left Neumann dimension of B op prime, and B op prime is it's the left Neumann dimension of B op, and B op is two unfactor acting on H as well. So it has that's how we define that. So that's what this means to be bifinite. Here's a proposition. So the product of these Neumann dimensions is equal to the index. So what I can do is I can take B op, which is acting on the left side and commutes with A, right? B op commutes with A, so B op prime is an algebra strictly larger than A, right? So A is contained in B op prime, right? So this is the Neumann algebra containing this one, just from the fact that the left action of A and the right action of B commute. It turns out that the index of this subfactor is equal to the product of these Neumann dimensions, okay? Now this right-hand side, by definition, we say this is infinity if B op prime is to infinity. It might be the case that that's a to infinity factor, so in that case, the right-hand side is just infinity. If not, then it's a 2-1 factor, and the index of the index of the subfactor is equal to the product of these dimensions, okay? So the proof of this is, I'll basically give you a very terse proof. It's that if I take L2 of B op prime, okay, as a left A module, and that's what you have to take the Neumann dimension of this Hilbert space in order to compute this index, right? Whatever this dimension is, I have to show it's the product of this. Well, this is canonically isomorphic to the fusion of H with H bar. Okay, and this is Sauvageau. Okay, so this is canonically isomorphic, and so because this is the left A action goes along for the ride, so the dimension here is the dimension here, and then you remember the property that the Neumann dimension under fusion and this left-right business under conjugate, we know how that behaves, and so this just gives you this as from there. Okay. Great. From this, you can talk about conditional expectations. I'm going to skip conditional expectations for now. I may regret that later. I'm going to move on to dualizability.
If the right-hand side is integer, then does this imply anything on the left-hand side?
If this is an integer, these might be square roots of integers, I guess. Let me see. I'd have to really sit down and think about. Yeah, and you should be able to concoct an example there, no problem. For example, yeah, you can take like an Ising category, and yeah, you can do that. That should be no problem. Nobody's seeming to argue with
Surely
these.
can't you just amplify and get the integer in any way you want as a product of two things? For sufficiently large integers.
You needed to start with something that was a square root of an integer in order to. I mean, the point was, if this is an integer, is it possible for these to not be integers, right? That's really the question, right? So
Or is it possible for those to be transcendental?
the product of two transcendental numbers to and then get an integer. I'm going.
Pi times, for example, 3 over pi gives you an integer.
Pi is not an index of a. It's not an index of subfactor. Oh, yeah, pi.
But
Pi times 3.
2 pi certainly is, right?
Yeah, yeah. Okay. Let's just. Okay, that's a good question, and I don't want to think about it right now. Okay. So dualizability. Let's talk about this for a second. Right. So here's the we say that right. Here's a proposition. So we take, if I have that the right monomial dimension is finite, so H here again is an AB bimodule. If the right monomial dimension is finite, this is going to imply that there exists an isometry from L to A to H box times over B with A bar. Okay, this is an AA bilinear. From L to A to H box times over B with H bar. Okay, so how does one go about doing this? And here's also if H is irreducible, the converse is true as well. Okay, so for an irreducible bimodule, if I have an A bilinear isometry, it also implies that this monomial dimension is finite. Okay, that's a bit trickier. I'm not going to do the reverse direction. That should be in the notes, but there you can. I think you should probably. That's going to be in Focus correspondences as well. But how would you do this forward direction? Because that's the thing we want to. We're trying to construct this this planar algebra. That's why I'm wearing my planar algebra shirt. Is because hopefully we'll see some planar algebras today. So how does one do this? If the right dimension of H, the right monomial dimension of H is less than infinity, there exists a finite set of vectors beta that live inside bounded vectors such that these left creation operators, so here I have these left creation operators, I take their adjoints. The sum here is the identity on H. Okay, and this happens if and only if for every C in H naught, I have that if I sum over beta with beta XC, this is my right p-valued inner product, I actually get my C back. Okay. So this is what's called it's just an HB basis. In particular, it's called an orthogonal basis if the L beta star are orthogonal projections. Okay, so you can find these things. These things exist. Okay. So that's the point. There's a similar statement here for left modules as well, right? There's nothing. I'm just choosing the right one because I only want to work with the left operators. I don't want to work with the right operators because remember there was that extra J that appears in that A-valued inner product. So I don't want to work with the J. I just want to have this one. So great. So now I can prove a proposition. Proof of proposition. Okay, so again, this is a very terse thing because hopefully I'm going to tell you the steps on how to do it, and then you can do this as an exercise. So step one, you say, okay, you say for every U in the unitaries of A, U beta is another basis. Okay. Okay, so that's step one, so that's hard to do. Step two, you say, is showing that this vector in here is acentral. Okay, so acentral, it just means that A commutes with it, right? So in particular, maybe I should give you a little definition. You know, if I have an AA bimodule here, we say zeta in K is acentral, and we denote the set of vectors A prime cap K if for every A in A, is zeta A. Okay, so, and that makes sense for AA bimodules. Of course, it doesn't make sense for AB bimodules. And note, there's an interesting fact here that it's a very fun exercise to prove. Here's a fun exercise. If zeta is in A prime intersect K, and remember A is a 2-1 factor, then it's bounded. Okay, it's a bounded vector. All right, and the hint is just that look at this vector, look at this state here, and then use unique trace. Okay, so look at that state, and then use the fact that a 2-1 factor has a unique trace, and you'll see that an essential vector is bounded for a 2-1 factor. Okay, so great. And what's next? Okay, so that was step 2, and then finally step 3. I mean, since it's acentral, you just look now at the map. A omega maps to this, and then that does it. Okay, so since it's acentral, this is exactly is about. This is going to be a bounded operator. It's going to go from L2A to here. It's going to be an isometry. It's not going to be. So you just that's what you want. Okay. So great. That proves this one direction of the proposition. I'm not going to do the corollary. You can, or the converse. You can check the notes for that. The corollary also to this is basically you can say the same type of thing. If this right von Neumann dimension is less than infinity, then that means that I get a surjective partial isometry from H bar, from here to L2A just by taking the adjoint, right? So that's essentially that's what I get, and then there's also great. And so here, this is just, we define this to be coev, this map is called coev H bar, and it's defined to be This is defined to be ev H bar, it's this coev H star, and this map here is this coev H. That's the name of this map that we were actually constructing here. This is called coev, the co-evaluation, L2A. All right, and here I just take the adjoint and I call that evaluation for H bar. Okay, so similarly, there's or a similar analogous result when the right von Neumann dimension is finite, and this gives us an evaluation map for H. L2B, and it gives us a co-evaluation map for H bar, which is just F. This is the adjoint of that, right? And this goes from L2B to H bar box times A. H. Okay, so what this does is basically tells us when we have these evaluation and co-evaluation maps. So it's important also to note, here's another exercise. When coev h bar exists, so ev h exists, so ev h here is this map here, which is going from h bar box n to h to L2b, it's given by so what do I have? I have some, I have to take bounded vectors here, both of these things, eta, you're living in these bounded vectors, and I guess it's for the right b, okay, if I have two bounded vectors, I need to tell you where this maps to, but it maps to the only sensible thing that you would write down, it maps to the b valued inner product. Okay, the b valued inner product gives you exactly this evaluation map, and that's why it's called evaluation, right? So you should be thinking in your head maybe like, take a finite dimensional Hilbert space, right? Evaluation there is the pairing, right? But here we have, it maps from the conjugate space tensor the ordinary space to a number, yeah? But here the evaluation lands in B. So this is the definition of why it's called evaluation. And co-evaluation is, the reason it's called co-evaluation is because this thing is actually independent of the choice of beta, right? That's also, this will be independent of the choice, right? This is actually a canonical map, independent of the choice. And this is very similar to things in finite dimensional vector spaces. And now we get to draw diagrams for these maps. So where are my diagrams? So here we have, remember, H was a string shaded on one side. So now co-evaluation for H goes from L2A to H tensor H bar, and it's read upward, and it looks like a cup. I have co-evaluation for H bar, so here I'm assuming now that we're bifinite. So H bar has a shading here. H2B goes to H bar H. Evaluation for H goes from H bar H to L2A. And then here, I go from H bar to L2B. Wait, what? I've done this. What have I done? H has A in here, and L, yeah, this is for the L2B, and this should be L2A. I have, unfortunately, on my sheet, I've reused these symbols, but I can't do that. Okay, so those are the diagrams. And the reason we draw these diagrams is that they satisfy what's known as the zigzag relation. Okay, so what's that? Let's draw some pictures. So the zigzag relation is as follows. So these Morse cancellation moves are satisfied, okay? And there's another plus the other shading. Okay, so what I'm going to do is I'm going to prove this one for us, and the rest of them you can check. So this map, so what do I do in order to read this map? I chop it here in the middle, okay? So first what I do is I take my bounded vector, C. When I have this co-evaluation on the left, I'm applying coev tensor id, and really I'm creating a pair on the left. So it maps to beta bar x times C. And now I'm suppressing the associator for my picture, and I'm also suppressing my associator here In this sum, really there's an associator around, but who cares what it is, it all works. And then, what do? I apply my evaluation map for H, which is just given by taking the p-valued inner product. But now what these betas were a basis, they exactly satisfy that this sum is, where is it? It's over there, right? This sum is exactly C. So this is exactly C on the nose, and I get the identity map, okay? And then there are, 3 other things to check, but they're all not so hard. They're the same thing. So definition, we say H is dualizable if these maps all exist. So if these maps here is, these 2 co-evaluation maps and these 2 evaluation maps. That's what it means to be dualizable, okay? And we see that, right, so we saw that this is the same thing as basically the following are equivalent. We see that we're dualizable
just to make sure I understand, before we would have had to have written the it at the top and the bottom, right? Because in the middle we have this co-evaluation stuff.
Sorry?
So
where?
in our proof of the zigzag property,
Yeah.
We would have had to have put our morphism so our bimodule at the bottom and the top in the left-hand picture.
Yeah, they are. It's H.
Yes. Okay. Yeah. Okay. Okay.
Yeah, this is for any H. This is, for H, yeah, I suppress the label. But it's there.
So the sum over beta is finite.
Sorry? Beta is a finite set.
Now, is it essential that this is finite?
No, it's not. And the notes will deal with the case where it's not. But in 2-1 factors, you can choose it finite, and that's so we do it. Just makes everything easier. It's like I said, we're assuming it's a 2-1 factor for technical simplicity. Finite sums are much easier than infinite sums. Okay, so here you're dualizable. That's the same thing as saying that both the left and right von Neumann dimension are finite by these propositions, right? So I guess there's an irreducibility here, but third you have this B f prime. This index is finite. Okay, so great.
So, sorry, the claim is that those are equivalent for an irreducible bimodule?
So these are equivalent. These are clearly equivalent. We already proved that these were equivalent,
Yeah.
2 and 3.
But
For an irreducible bimodule, yeah, so all these maps exist and they satisfy zigzag.
what happens in a non-irreducible case? Is there actually a difference?
No, I think you can, it's a good question. We'll talk about it later. Okay. I don't want to, so I haven't said TFAE here. Certainly the second 2 are equivalent. We proved that. That's the Sloboshov proposition, which I erased. Certainly this implies this, and this should imply, the problem is it's really this plus zigzag, I think. Should
2 implies 1 shouldn't really require irreducibility,
2 implies 1 shouldn't require, no, we already proved 2 implies 1 without the irreducibility.
right?
That's what we actually proved.
Right, okay.
Yeah.
Didn't we just prove that if they exist, they satisfy zigzag?
No, the ones I constructed, right? The ones I constructed from here satisfy zigzag.
Okay. Yes.
That's what I proved. No, it's not if they exist, then they, right, oh, I see, yeah, when it exists, what did I say?
That
Well-
when exists is the thing you constructed there, right?
When coev exists and given by this formula. Yeah, in this case, that should just say, when it exists by this formula, it's given by that.
Yeah.
So I need this formula in order to calculate it, and it's that. That's a very good question, yeah. Sorry, I wasn't as clear with that as possible. Now, the interesting corollary to being So really, this is saying bifinite is really the correct thing here. Right, these are equivalent to saying bifinite, and bifinite implies dualizable, and you should be able to show dualizability implies bifiniteness as well. But I have to think about that a little more. So here's a corollary. Here's actually a theorem, and it's by Jones. It says that if A contained in B has finite index, then A prime intersect B, the relative commutant, is finite dimensional. Okay, it's a finite dimensional Penneys algebra. And what this implies as a corollary is that if I have a bifinite bimodule, that implies that B op prime, right, I have this index is finite, and that implies that A prime intersect B op prime is finite dimensional. And what is this? This is exactly the endomorphisms, the AB endomorphisms of H. Okay, so this says that the endomorphism space is a finite dimensional Penneys algebra for any bifinite bimodule. In particular, since it's finite dimensional, it's semi-simple. As a complex algebra, and basically what this tells us H, this is the statement Yasu said before. I have a finite direct sum. I can write H as the direct sum of Ni, Hi, where all of these are irreducible. Okay, so fantastic. Bifiniteness implies this. Great. From this, right, so also from dualizability, we can prove Frobenius reciprocity, the theorem that Yasu talked about yesterday. So the Frobenius reciprocity theorem says, suppose we have an AB bimodule, a BC bimodule, and an AC bimodule with K, BC dualizable. Okay, then there exists a basically natural isomorphism from Hom. This is an AC linear map from A box times K to L. Okay, this is isomorphic to naturally isomorphic to Hom AB from H to L box times over C with K bar. Now what's the map? Here I'm using dualizable. The map is just if I take F, all right, here remember B had this shading, C had this shading. Where does it map to? I just take the string and I pull it up. Okay, and you can write down the inverse map, and then the exchange relation together with the zigzag cancellation tells you that this really is an isomorphism. So that's the proof of the Frobenius reciprocity theorem. And there's another thing you could do. If H were dualizable, you can move that as well. Okay, just by pulling the string up on the other side. All right. So now we're almost there to our planar calculus. Almost there. The last thing you might want to do in planarities, you might want to start rotating. Okay, you might want to do some kind of 180-degree rotation. All right. So here's the proposition. Let H and K be bifinite, in particular dualizable. Okay, and let F be an interpointer. Okay, then if I take F, I do this. So here's my H, here's K. These are now, B is now on the left-hand side, and this is now K bar, this is H bar. Rotating this way is the same thing as rotating this way. Wait, what have I done? Alright, so here's H bar, and here's K bar, and it's equal to the map F star bar. So it's the conjugate of the adjoint, all right, and this is also known as F star bar is also known as F check, and note that F check, the map F goes to F check is linear, right? Because I've done two involutions, therefore it's a linear map, but it turns out that this is going to be contravariant. It's a functor, but it's contravariant if I do it, right? Because bar preserves the order of composition, but star reverses the order of composition. Okay? That's the issue here. All right? Fantastic. So what's the proof of this? Well, I'll do the left-hand side. We'll show that this is equal to that map. Well, I have to say what it does. What does this map do to something in... So if I pick eta in K naught, well, I need to tell you where eta bar goes to, because it's starting in K bar, okay? Well, I take eta bar, it goes to sum over beta. That's the first thing I do, sum over beta. Eta bar, box times beta bar. Okay? Then where does it go to? I'm reading upward. Right, it's three different maps that I have to apply. The next thing I do is I apply F to the middle. Okay? So I know how to apply F, and then the last thing I have to do is I have to cap here. Right? This is now the capping in K. This is the same thing as here this becomes eta bar. This is at the eta. Now it goes away, the bar goes away. Okay, so that's what I get. But now I have to do a little bit of I have to manipulate the symbol just a little bit. So the F moves over here as an adjoint. So this is an exercise that you're allowed to do this. And now this, remember, the action on the conjugate is just action on the right by the adjoint. So it's beta, but it's on the, and then I take the adjoint of this. When I take the adjoint, it flips it. Okay. What's that? When I sum over beta, that's exactly the defining that's the basis. So it says F star of eta bar, which is F star of eta, it's F star bar of eta bar, and we're done. Okay? So that's the proof that the left-hand side is equal to F star bar. You do the other side, but you need the basis on the other side, okay? If you do, you're going to need the left A basis rather than the right B basis. But these things exist because I've assumed it's finite, okay? So you'll do it the other way, it'll be in the notes. Maybe I'll just have also just this in the notes. So it'll still be left as an exercise for doing it the other way. Okay, so this is what's known as pivotality. This is the pivotal structure. Okay, there's a pivotal structure.
Is F supposed to be the pivot when going around, or
Sorry?
what's the pivot?
Yeah, it's saying that I can rotate this way, right? It's I can
twist that.
I can twist this way or I can twist that way, and I get the same thing. It's pivot. That's the pivot. That's what it means. Pivotal. Okay, and great. That's pivotal. Fantastic. And now I can talk about. Here's the definition. You have to be careful here, because you can get into a little bit of hot water if in in C-star tensor categories, this thing is using the pivotal structure that comes from the category of bimodules over a 2-1 factor. Now, for anyone, this is just a sentence for the experts in the room. A rigid C-star tensor category has a canonical bi-involutive structure where that's always spherical. And even if you realize it as a category of bifinite bimodules over a 2-1 factor, that spherical structure may not agree with this pivotal structure. Okay, so that's something to be careful about. Okay, the canonical bi-involutive structure on a rigid C-star tensor category, this is like the minimal index that Yasu's talking about, and this is not coming from some minimal thing. This is, you know, this thing coming from that's coming from the 2-1 factor land where things are not always extremal. Okay, so that's just anyway. I just wanted to say that. Okay. So this is spherical or extremal. These are both the same thing if for every f in the AB endomorphisms of H, you have the following equality. So this, whatever this is, this is a map in end of L2A from A to A. Okay, this is isomorphic to the complex numbers, which is isomorphic to n BB of n and B, and I have something else that I can put in there. I can take f, I can do the cap the other way. These have to be equal. If for everything this and this agree as numbers when I push them over here, and the map here is the identity L2A maps to 1, and that's also where the identity in L2B comes in. Okay, so under the map that sends the identity to 1 and the identity here to 1, if this number equals this number, that's what's meant as spherical. And the term spherical comes because you should think about now isotopy happening on a sphere, right? I can take this curve and I can maybe, if it were on a sphere instead of a blackboard, I would rotate it all the way around the sphere to the other side, and I would end up with this picture. Okay. The word extremal is another word that I'm going to give a post hoc definition of it. Extremal could be saying, well, this is the minimal index, right? And so it's extremal in terms of index as well. So that's another. Anyway, that's great. Fantastic. So here's an example of something spherical. Here's an exercise, rather. So suppose HAA has a real structure RH, which is, remember, this is a unitary from H to H bar such that R bar composed with R is the identity. Okay? Then H is spherical. Okay, so if you have this this real structure, you can this can be used to get a spherical structure for H. Maybe not H is spherical, it's maybe bad. You should say you can make H spherical. Okay, so what do I want to say here? Yeah, you can use R to make it spherical. What am I saying? That's not true. I'm going to erase this because I don't want to waste time, and there was something else I was going to say here, but really what I was going to say is, let's put a line here so it's separated from spherical. If HAA has real structure R, then one can calculate that this is true. So if I take R, but I rotate it, as a map H bar and I have h down here, and I have h bar over here, this is the same thing as r. Okay, so this is saying it's a real, this is like real versus pseudo-real for self-contragradient. Okay, for those of you who know what that means. But the point is that if I rotate r, I get the same thing back, and this is exactly this condition together with this is unitary. Okay, so this is an exercise, and I wanted to say something about sphericality, and I'm just drawing a blank right now, but I really wanted to say something about that. Okay. Yeah, I just don't want to make a mistake for all of eternity on the internet. Okay. All right, so now we can actually go back to subfactors and standard invariants. So we haven't, this has been a course on subfactor theory, but so far I've done this two-category approach to it, and then, with bimodules, now let's actually study a subfactor from this perspective, okay? The goal is working toward this planar algebra, which I'm going to get to. I'm going to write down a planar algebra picture today, hooray. So, I'm going to start with A containing B, a finite index to one subfactor. And then from this I can form the standard bimodule, which is L2B as an AB bimodule. Now in Yasu's talk, maybe I should use should I use the same, let me use the same notation from Yasu's talk. In Yasu's talk, this is rho bar. This was, I'm going to differ. I'm going to use rho instead of. Let's write that on the board. Okay, so that's our standard bimodule rho. And then, again, the index, right? What we're going to do is I can take a category, this two category, A contained in B, is the two category generated by rho and rho bar. And what do I mean by that? What I do is I take the objects are going to be A and B, okay? And remember, there's unique traces, so I don't have to specify what they are. One morphisms, they're all bimodules generated by rho and rho bar under the following operations. I have diffusion. I can take direct sums. I can take conjugates, and I can take subbimodules. Okay, so I'm going to take all the bimodules generated by this, and then the two morphisms are all the interpolars. Okay, so really this is just one operation. I should just write box times. But you can't box times, anyway, that's just one composition. Great. So for example, if you can think about this as I'll have AA things, AA bimodules, AB bimodules, BA bimodules, and BB bimodules. And if I took an AA bimodule and I wanted to get an AB bimodule, you would do this by fusing with rho on the right. So if I that's the same thing over here. If I took an AA thing and I wanted to get a BA thing, that would be fusing with rho bar on the left. Okay, so in particular, the AB bimodules, to get all the AB bimodules, I just look at, well, rho is an AB bimodule, but so is rho bar to the end rho. And in fact, if I decompose these into irreducibles, then I get all of the AB bimodules that I'm going to get this way. Okay, that gives me all the irreducibles. And Yasu yesterday constructed the principal graph and the dual principal graph from these irreducible bimodules. So I'm feeling inclined to skip principal graphs, and maybe we'll return to that on Monday on the last day if we get there. Rather, I'd like to actually build planar algebra now and talk about what planar algebra is. Okay? Any questions? Now's a good time to ask. It's okay? Okay, so now let's talk about planar algebras. Great. So from this two-category formalism, we can define planar algebras from our favorite, looking at our favorite subcategories of these things, our favorite things generated by certain one-morphisms. So a planar algebra is a sequence of complex vector spaces, Pn. So what I'm going to do, first thing I'm going to do a warm up here, which is unshaded, unoriented. It's a sequence of complex vector spaces, n greater than or equal to 0 here, together with an action of unshaded, unoriented planar tangles. Okay, so this is a definition which requires another definition. Okay, so in order to tell you what you know what a sequence of complex vector spaces is, no problem there. But I have to tell you what do I mean by a planar tangle and what do I mean by an action of these planar tangles. So to do that, let me do a definition by example. So a tangle is something that looks like this. Okay, so the features of a tangle are that it's like a spaghetti and meatball diagram. You've got a big plate, you've got some meatballs on it, and you have non-intersecting spaghetti, and that spaghetti either joins the plate to the external boundary to the external boundary, or the external boundary to one of the internal boundaries. And there's also these yellow stars here. These yellow stars are only important here for composition, all right? So this is a tangle. Something like this is a planar tangle.
In the columns?
The colors, so the white stuff is disks. Everything in white is a disk. So it's a big disk, small disks inside it. The yellow things are strings, which are non-intersecting, and all of the boundary has to be contained in the white circles. So they can be free-floating, and that's fine. Okay, but a free-floating yellow string is different than a white disk. That's why I'm using two colors. Okay, so this is a planar tangle, and this has to give you a map amongst the vector spaces. So here, I'm just going to order these 1 and 2. This is a map, a linear map from P3 tensor P2 to P5. There is some map, right? The planar algebra gives you the data of some map amongst these vector spaces for each tangle. Okay? What does it mean that's an action? Here's another thing I could write down.
How do you count the index of P?
Oh, sorry, yeah, okay. Thank you very much. I went way too fast. Well, I look at, this is 1 and this is 2. So the first space, this is going to eat some vector from one of these spaces. What I do is I look at the number of strings touching the boundary. I get 3. That tells me the index is 3. Here, it's 4. Oh. I was getting ahead of myself from down here. Okay, so this is going from P2 to P4. Okay, then I can talk about the composite tangle. there's only one place I can glue this. I can glue this into here. What I do is I take this, I shrink it down, I glue it in, and I have to make that the yellow stars align. That's the point about the yellow stars, right? They tell me how to align the boundaries before then I'm going to remove this white thing and then smooth out the strings. So a picture is worth 1,000 words in this case, so let's just draw the picture. So T look like this. And then I draw S inside. Right? And then, after I do this, I go ahead and I remove stuff. Okay, so I'll just leave it dashed here so that you can see where it used to be. Okay? So whatever's left over is T composed to S. Okay, now everything is up to isotopy.
Can you have 2 times disks with the same numbers of strings?
Of course.
So when you compose, then it appears.
Well, then you have to say where you're composing. I'm composing in disk 2. Yeah. In this case, there's only one way. Another viewpoint just says that anytime you compose, you have to have a disk to glue into every disk at the same time. So everywhere else you're gluing in identity tangles, which are just some radial strings. That's another way that you could you can avoid that problem of saying which thing, where am I gluing into? And in fact, that comes in with the thing I'm about to write down here. The action means that this has to, composition of tangles has to be the same thing as composition of linear maps. This is going here from P3 tensor P2 to P5. Okay, so what this says is P3 tensor P2 to P5. Here this is T composed to S. Here I'm going to take the identity tensor S, going from P3 tensor P4, and I'm going to do T, and this has to commute. Okay, so here, when you're talking about the action, you really have to glue into everything at the same time. If you want to take linear maps of tensor products, otherwise you have to talk about composition of multilinear maps, and that's fine. You can do that too, and then specify where you're gluing. But these are 6 of one, half a dozen of the other.
What do you do with the floating zero?
It's just a string. It's just there. The point is the planar algebra comes with the data of any planar tangle is some map.
Oh, so we could have started with one.
I could have started with one and then it just goes along for the ride. Let's work out a specific example of a planar algebra, okay? To see how this works. So this is called the temporally Jones planar algebra. TLJ of delta. I'm going to give you, again, a definition by example. So TLJ6 is the complex span of, well, there are 5 tangles which make up the complex span, or that make up the basis. Okay, so the basis consists of all ways to pair 2 endpoints with non-crossing strings. Okay, so TLJ odd is then 0. Okay, for every odd box space, I get 0. All right. So what I have to give you is an action of planar tangles. Well, because they're presented by tangles, what have I done? Because I presented this in terms of planar tangles, the action is really easy. All right, so here's an operator, some planar tangle, some annular tangle. It goes from P6 to P2. Let's plug in something in my basis. Okay, inside TLJ6, P6. How does it act? Well, I already told you how tangles compose, so they do that. You glue it in. Now, the problem is that does not live in TLJ2, right? So this here is some tangle T, this is some element of TLJ6, and this is just a tangle, right? We need to figure out, it's not something in TLJ2, so what do? There must be some rule to force it into TLJ2. What I do is I look at the closed strings. Every time I see a closed string, I take it out for a multiplicative factor of delta. And now I'm happy again. Okay, so great. So that's the action. That's how it works. Fantastic.
What does delta mean?
Delta is just some number that comes along for the ride. Delta is a complex number.
So this was that?
Sorry?
So what did we do here? We took a tangle.
I took a tangle, I glued it in, right?
So we're showing an action
I'm defining the action, and I'm just saying how does it work.
of who on, so something on
Of a
TLJ6.
tangle on something in TLJ6,
Okay.
on this guy here. And similarly, you can work out how to glue in every other basis tangle. Since I've told you where this map takes a basis, I've told you the linear map.
This is all tangles acting on TLJ6.
This is this particular tangle.
Oh yeah,
But you can take any tangle you want to now, and you can compute its action. And because it's gluing tangles, and gluing tangles is associative on the nose, this is an action. Right? Everything is manifestly associative. So I'm gonna push through and finish this page. Here are some properties, because I want to get to a punchline. The first is that there's an associative multiplication on TLJ 2n. So let's just do the 6. This tangle gives you an associative multiplication. And the point is that, and that's an exercise, the point here is just that I can glue this way, right? Or I can glue the other way, and they're going to be the same thing, because both of them are the same thing as the same tangle without. Okay, so this gives me an associative multiplication on TLJ. 2, there's an adjunct which is given by white star instead of yellow star. It's the conjugate linear extension of reflection. Okay, so this idea of reflection being an involution and being conjugate linear. Okay, that's one of the things, one of that's been one of the themes here. And 3, there's a trace. There's a trace of 6 of an element x. It's given by taking x. Now x you can think about as something that has, it's a linear combination of these diagrams. This diagram here, I'm just capping off everything. This lives in TLJ0, which is canonically isomorphic to the complex number, via the empty diagram goes to 1. So in particular, you're never allowed to write 0. I should write TLJ sub 0 instead of actually writing a 0 there, because it's hard to tell 0 from the empty diagram. So that's a trace, and the proof that it's a trace is a nice exercise here. It's just that if I take x and I take y, okay, just move this guy downward. and move that guy over that way, and it goes up that way. Okay, so this is tracial. The punchline of today's talk is the following theorem. Due to Jones. This is the Jones index rigidity theorem. Okay, so this says the following. I can take an inner product on xy2n, or a sesquilinear form, rather, given by trace 2n of y star x in this usual GNS way that we talked about on the first day, and that Yasu also talked about on the first day. If I look at this, this is positive semi-definite on TLJ 2n for every n greater than or equal to 0, if and only if delta is in the set 2 cosine pi over k, such that k is greater than or equal to 3, or bigger than 2. And you'll notice that the corollary of this is that the index of a subfactor, so this is the original thing that Jones proved, but what he proved is a statement really about these temporally Jones algebras. That's why it carries the name Jones. This index lives in this set 4 cos squared pi over k, so k is going to equal to 3, union 4 to infinity, but now the subfactor is allowed to have infinite index if we wanted to. Okay, so that's the punchline for today, and next time we'll talk a little bit more about planar algebras, but subfactor, well, how to build them actually from categories, because we didn't actually build anything today, we just talked about the temporally lead one. Okay, temporally lead Jones. Thanks.
Are there any more questions or comments? If not, we
So if
can-
you put them incompatible, like if we just take that tangle and get rid of one of the,
You can't glue it in,
so
because it doesn't act on it.
there just is no action.
I mean, the point is that the tangle is a map from, this is a map, this T is a map from P3 tensor P4 to P5. So I can't plug something in that's not in P3 or P3 tensor P4. It's just, that's not the domain of that map. So it doesn't make sense to plug in the tangle that's not in that domain. Right?
I mean, if I just look at the definition of planar algebra, is a sequence of these spaces with an action of these planar tangles.
Yeah, the action mean, I mean, this is a very wishy-washy definition that I've given you, right? I've said it's an action of planar tangles. What does that mean? It means every tangle that's something that looks like this gives you a map among the algebra, it gives you a map
Okay.
amongst here, and that map, you read the domain by looking at the number of
Oh yeah,
strings.
yeah, sorry, yes, okay.
So that's the, I mean, it's,
Okay, yes.
Any more questions? Not, we'll break for 2 minutes.